Okay, so what I've got for this time slot is actually a very short lecture on something that I consider a miracle of optics, and that is the way Fabry-Perots play the role of beam folding systems, even though you cannot spot any discrete bounces. They're all superposed together. Um, when when I had prepared this lecture before, I also had some material on Pound-Weaver Hall locking, but we have talked about that a lot, and I decided not to go through yet a third presentation on Pound-Weaver Hall locking. So uh, this is it's fortuitous in a way, since after my short lecture, there are still two to be given by Rana, but this will make it so that we'll more or less fit in a reasonable amount of time, I think. Um, so here's where we are in the week. Um, I'll do a little bit of discussion of, or a reminder of why we are multipassing in our arms in the first place and why we don't do more of it. And then I'll have my little analysis of Fabry-Perot cavities, and I won't cover this material on reading out a cavity. So here's a slide that I showed before when we were first, this was Monday afternoon when we were talking about how a gravity wave interacts with an interferometer, and why it's a good idea to make your arms longer, even if you can't make them physically longer. You can make multiple bounces in an arm and build up more optical storage time and accumulate, at least in some very important limits, accumulate more signal. Now, the signal doesn't grow without limit. If you have a signal with a certain period and you build an arm with a storage time much longer than that period, it hasn't helped you. And the hand waving way to see that is if you're doing that integral of the amount of time it takes for a wavefront of the laser light to go through the arm, in the time it takes the wavefront to get all the way through the arm has changed its length. It's grown and maybe shrunk, maybe grown again. So in that limit, you don't win anything more. So that's one thing to know. Another thing to ask is, given that we have that we can use this trick of multipassing, why did we bother to spend so much money on arms as long as 4 kilometers? And the answer is, if we only were dealing with shot noise, we shouldn't have done it. But since we have seismic noise, I talked about this morning, and thermal noise, as we'll talk about tomorrow, those you only win with the actual physical length of the arm. Multipassing doesn't help you. So the design rule is, in general, you ought to build an interferometer as long as you can afford, and then make up whatever remaining factors to the ideal storage time using some sort of multipassing scheme. And the one that has proven to make the most sense is the Fabry-Perot cavity. I like that Rana showed a picture of Michelson and Morley's apparatus. I have a few more that clarify the point of what he was doing even more. And when you look at it, and I'll flip to those pictures in a moment, you'll realize that this was a heroic effort on Michelson's part, and it's a good thing that for our application, the Fabry-Perot cavities have come along. And he had to hire an assistant, Morley, and took them 6 years to do better than Michelson's original 1881 paper. I'll come back to my remarks about the equivalent that was being considered in our field in a moment. Let's look at the picture. So this is almost precisely the picture that Rana showed, except Rana showed it in photograph form. But in the journal where the 1887 paper was published, it wasn't so easy to publish photographs, so I'm pretty sure that this tracing from that photograph is actually what appears in the paper. And because it was traced by someone who knew what he was tracing, it actually clarifies things that I couldn't see so well in the photograph, namely all these optics mounts that Michelson invented for this purpose, which are pretty beefy, and even drew in the bolts that hold things in place. It's actually a really nice thing. And here's a plan view that also appeared there. And I believe this is the port where the light went in. Here's the beam splitter. Here's a compensation plate. Here is a way of tuning one arm length to make the arm lengths match, a knob and a screw. And this is the telescope that Michelson used to observe the fringes. So look at what he and Morley did. Laid out all these things and aligned all these darn mirrors. And students, you were aligning several mirrors and taking some care to do it. This was real work. But the advantage was, I mean, Michelson knew he needed to do it, right? Because he was interested in this ether drift effect, built his original interferometer on this table, but with just the arm lengths that he could fit on the table, and then realized that his sensitivity was not sufficient to resolve the ether drift effect at all. Basically, his noise was just about, you know, he was looking for a 1 sigma effect or something. Couldn't do it. So he knew he could see at the 10 sigma level what he expected, or rule it out at about the 10 sigma level, which is what he ended up doing. And raise your hand if you've read the 1887 papers. Anyone done? Okay, a few of you. Good. It's worth doing if you can get a hold of it. I read it from a paper copy in the geology library at Syracuse. It must be online somewhere. It is. Ron has read it online. Okay. Then I can assign it. It's a wonderful thing. He explains a lot of detail. It explains how they switched light sources. He used how they did the matching of the arm lengths. But the thing that I found most interesting was that Michelson didn't conclude his story the way we conclude the story on his behalf. He didn't say, I have shown that optics is in a complete mess because I ought to have been able to see the ether drift, and I did not see it. There's a crisis in physics. That's what we think he said. What he said was, you know, it's kind of a puzzle, but I'll bet the problem is that the ether gets entrained with the Earth's atmosphere. So since that's a problem, or at least I think it is, I'm going to redo this again on a mountaintop where there's much less atmosphere above, and invents all these excuses so that he doesn't have to say that he actually had an interesting result. So I think that's, to me, that moral lesson is at least as interesting as the technical lessons that you will also get from reading that paper. All right, I did want to make one remark about the proposed applications of this technology in the gravity wave business. I actually know of 2 serious proposals in early days, that is to say, in the 1980s, for doing discrete bounce folding in gravity wave interferometers. The MIT group of which I was a part back then was very fond of the Harriot delay line, which is a scheme for putting multiple spots in a circular ring on a large mirror. You have a large input test mass, a large end test mass. The light goes in through a hole through the substrate and the input test mass. And then if you find a fortuitous combination of mirror curvature and spacing, there is a discrete number of spots that fills up a ring before a beam comes back to that input hole and comes out. And at the scale of tabletop experiments, they've been built all the time, and they do work. but the scaling is very unhappy to the size of things that we need to do. You know, we have spots this big to make sure that input hole didn't clip the light or diffract it too much. The hole has to be like this big. The mirror ends up being this big. It weighs a ton or multiple tons. It has very low frequency internal normal modes. The engineering to support a mass that great with seismic isolation of the technology, the style of technology that Rana and I were talking this morning, was much more difficult than we allowed ourselves to admit at that time. And I don't think in retrospect it made much sense. There was a much more short-lived idea that was momentarily, for maybe a half a year or a year or so, proposed by the German group that they called the Schellenbaum idea. And it was really the, Rana, you haven't heard this, okay. It didn't last very long, but it was kind of cute. It was really to be the pendulum version of the Michelson-Morley thing. Discrete mirror for every bounce. And the advantage was you only had to engineer ways of holding individual small mirrors, but you did need a lot of them. And because they were small mirrors, you didn't have the very low frequency internal resonances that would be a problem with the very big mirror. But the main problem was the same problem Michelson and Morley had, namely all those things to steer. And so the idea died, and it's fine. It's fine that it died, I think. Yes? I'm not sure my memory includes that, but maybe they did.
There was a proposal from them
The Galileo proposal
for LIGO.
for LIGO.
There was an advanced LIGO thing, which was a sun calculator.
Oh, right. Okay. Now, okay, and with the Sagnac, there are some other advantages that made it maybe not quite so ridiculous. Okay, so it's had an afterlife, Rana is reminding me. Okay, there are diagrams. Now I want to say just a bit about how Fabry-Perots do this job. And with so many optics experts in this room, I kind of feel embarrassed to walk through this, but there might be some of you who would like a patient statement of this, so let's just go through it, and if it's helpful to you, great, and if it's just something that you've known for years, I won't take that much time with it. But I have to say that I, as someone who grew up looking at beams doing this, the idea that interference actually, in a tremendously meaningful sense, actually traps the light for multiple round trips, I still find mysterious, eerie, a miracle. I don't know what the right word is. And so I want us to walk through that just because I enjoy it. All right, and I'm going to shamelessly borrow some slides from a friend of mine, Joe Kowalik, who worked in this field for a while before moving on in his career. And let me illustrate a Fabry-Perot cavity. Here's an input mirror, output mirror, separated by a distance L. And we're going to consider an incident electric field, and we're going to follow what happens to the light as it arrives here and does some reflecting, does some transmitting, and all the reflections and transmissions, and finally consider especially the reflected light, because this is the light that returns from the arm towards the beam splitter. So the things we need to pay attention to are the electric field transmission coefficient and reflection coefficient here, and the electric field transmission coefficient and reflection coefficient at the end test mass. And we're going to start by saying, okay, our incident field is just some sinusoidal field at this very high frequency that makes it a beam of light. And now ask ourselves, what happens to the light after it arrives at this input mirror? And in particular, we'll be interested in the reflected light. So the reflected light includes some light that reflects promptly off of this mirror. Here's that term. It's just the incident field times the field reflection coefficient. The light that isn't reflected enters the cavity, so it gets multiplied by the transmission coefficient T1, propagates here and picks up a phase appropriate to traveling a distance 2L, gets multiplied by the reflection coefficient here, and again by the amplitude transmission coefficient here, and gives a net contribution to the reflected field of this term, E naught R2 T1 squared e to the I omega t minus 2L over C for the phase from traveling through the cavity. And then the light that isn't transmitted doesn't pick up that second T1 yet, but it picks up a second, it picks up an R1, another R2, and then finally a T1 here, except this light has the phase appropriate to having moved a distance 4L. And then there's the 6L, and look at the pattern that we've got. We've got R2 T1 squared, R2 squared, T1 squared, R2 cubed, T1 cubed with an extra R1, R1 squared. What we've got is a power series that we can sum. Here it is, factored a little nicer to make the mathematics jump out. Here it is as a power series, and because we know what the sum of a power series is, we can find the answer for the reflectivity, for the reflected field, and we see that, okay, it shows it carries these reflection and transmission coefficients, depends on, has a phase that depends on the length L, and because that phase-dependent term shows up in the denominator, and because R1 and R2 are typically close to 1, we like the application where R2 is as close to 1 as we can make it, and even R1 is not so far from 1. This can, for the proper L, give us the sign that gives us a denominator that shrinks to something really small, and this is the resonance that traps the light. But if we pick a different length L, the light isn't trapped. If you do the same thing for the transmitted light, you can see directly, because there's no R1 term here, you can see that the transmitted light grows in amplitude dramatically, and that's stating that the power is building up in the cavity, because all those round trips superpose in phase. Now, the thing that we care about is whether we have found a way so that for a given motion of the end test mass with respect to the initial test mass has the phase of the light that returns to the beam splitter, is it much more sensitive to that than just as if the light had gone one round trip. And so graphing the phase of that reflected light from that formula on the previous page, here are a couple of examples with less and less loss, higher and higher reflectivity in that Fabry-Perot cavity. And you can see as we increase the finesse of the cavity, the dependence of the phase on cavity length becomes something very steep. And that is the thing that is the equivalent of having made, or is the thing that makes this equivalent to the light having made many round trips. But now here's the terrible thing. We've talked about this before. In fact, Ramanna sketched this just before we broke for lunch. We have this nice linear and steep characteristic in a very, very small range of cavity length corresponding to the resonance. And everywhere else outside it, there you have nothing like that steep dependence. So thinking back to why this scared a few people like me back in the old days. This is just a reminder that you have to already get the cavity working before it's working, which is to say you have to find a way to bring those cavities into the right separation so that they resonate, and then and only then do you get the effect that you wanted to get. Some of us were brave. Some of us were fearful about this. The people who were brave were right. Okay, so those are just the words that I just said. Now, I just want to remark about one other fact before I turn the stage over to Rana, and that is I want to point out that the calculation that I just walked us through was for DC, or very, very low frequencies. And it's a more involved calculation that I'm not in a position to walk us through that that considers what happens if the motion of the end mirror, if the length change happens at a non-negligibly low frequency. Let me just state the result, that you get the same response as I showed the calculation for, except multiplied by a characteristic of a low-pass filter. That is to say, the response starts rolling off above a frequency F cavity that depends on those reflectivities. And it's something that is small compared with the free spectral range when those reflectivities are close to 1. It makes a smooth one-pole roll-off. Now, it's a very benign kind of effect because if you increase your reflectivities to try to build up your storage time, you don't actually reduce your sensitivity at high frequency. You get all of the response to a gravity wave you possibly can at high frequencies, but instead you build up your DC response only at a narrower and narrower set of frequencies close to DC. So you're invited to do this if you think it will help. It doesn't hurt you. Now, there's just one last thought that I'd like to leave you all with, and that's something that, until I worked it through, puzzled me a certain amount, but I hope to make it obvious to you as it eventually became to me. And that's the question of, we know that shot noise is white. The shot noise in the power in a laser beam falling on a photodetector has a white power spectrum. There's no characteristic time, there's no memory. But every time I look at these noise graphs, okay, if I erase this. So I look at a noise spectrum. I always see this thing that's proportional to F, and somebody tells me, oh, that's the shot noise. So the shot noise, as we express it in this amplitude spectral density of noise expressed as strain noise, isn't white. How can that be? Well, it's not really a big mystery. It comes precisely from the fact that your response to a gravity wave is rolling off at high frequencies from those arm cavities. The noise is white, but at higher and higher frequencies, a given amount of noise has to correspond to a larger and larger H to have competed with that noise and come over it. So that every time we're seeing this shot noise part of our noise spectrum rising like 1 power frequency, what we're seeing is that frequency dependence of the cavity pole, reminding us that we don't have arbitrarily good high frequency sensitivity. So in case you wondered about that, that's what that was about. Okay, so that's all the material that I've prepared, and we can move on to the next topic if people would like.